How will we go with this? What is a brute force algorithm? It's going to exhaustively enumerate all possible peptides of a certain mass, and then it's going to figure out which one's spectra, theoretical spectrum, matches the input spectra that is given to us. Okay. So, the mass of the entire peptide is usually known. So, this strategy would work then. You generate all peptides with a given mass. In this particular case, the tyrosine B1's mass is 1322. So, you just know the mass of the overall peptide. The mass spectrometer usually gives you that value, right, if you do not fragment it, and then form the theoretical spectra, right, of each of these peptides that matches this mass of 1322, and then look for the matches with the given input spectrum. Okay. And so, whenever the derived theoretical spectra matches the input spectrum, those are the peptides that will be output as a solution. But what is the problem with this? You will have like many peptides with a particular mass. Okay. If you look at the integer mass here, 200, 400 and so on, 1322 is going to be somewhere over here, right, and then you are going to have about 10 to the power 14 peptides that will have a mass of 1322, right. The larger the mass of the peptide, the harder the problem is, because there are many peptides that will match the same mass. Okay. And just to give you an example, here are two different peptides, NQEL and TMDH, that will both add up. The total mass is going to be 484 here, and then the total mass is going to be 484 here, right. In the previous plot, 484 corresponds to somewhere over here. So, you have 10 to the power 4 peptides that have 484 mass, but then in terms of a tyrosine P1, you are going to have trillions of peptides that will have the mass of 1322. So, it is going to be a really slow algorithm if you are going to go over each one of those trillion peptides and then try to figure out its theoretical spectrum and then see if it matches the input spectrum. And what does this processing of each of these peptides involves? It involves taking this particular peptide TMDH or NQEL, these candidate peptides, breaking them down into all possible substrings, including the empty substring and the full string, right, and then computing all their masses and then trying to see which of these mass spectrum, right, matches the input spectrum. So, we have in this case these two different peptides that have the same total molecular mass 484, right, but then the individual substrings masses are entirely different. They have completely different spectra, and only one of them will match the input spectra. In this case, NQEL is the input spectra, so only this will match. Okay. Can we get at NQEL faster than trying all the 10,000 other peptides that have the same molecular mass of 484? Okay. Can we somehow build the actual peptide, reconstruct the peptide from a small peptide and slowly grow it until we reach the full length peptide? Here we are trying to guess the full length peptide right away and then trying to match its spectra, but can we, instead of doing this top down fashion, can we go from a bottom up fashion? We start with single amino acids, then we grow it into 2 amino acids at a time, and then so on until we get the full length peptide. Okay, and that is the branch and bound algorithm that we are going to look at next. The idea is to slowly build up candidate solutions from smaller linear peptides, and that way we can try to see if there is any speed up that we get from running the algorithm to construct the full peptide. So, we will start with these small peptides, and then we will branch and try different ways of growing this small linear peptide into longer peptides, and then some of them will work, some of them will not work. So, that is the bound part. So, you just branch it and then you bound certain things, you prune certain leaves. So, this one didn't work, and so this one removes, and then only these 2 leaves are there, right. Then once you have bounded, then you again grow it into a bit more longer peptides. So, that is the branch part, right, and again out of these branches maybe these 2 branches do not work, right, and so you just prune that, and then you only look at, that is a bounding part, a pruning part, and then you look at only this one, and then you keep on going, and these are the candidate solutions that you have that you can then inspect for the full spectrum. Okay. What does it look like for this particular example that we have? This is our full spectrum that we have, which is the masses of all substrings of some unknown peptide, right, and then we can start with the smallest possible peptide, which is a single amino acid, right. So, you can compare it with all the amino acids that we have. These are the amino acids and then their masses, and we can look at what are the ones that are matching here. Okay. So, you can see here for instance that there is 99, so 99 is matching here, right. There is 97, so 97 is here, right, and there is 101, 103, so these are matching right? So you can say that maybe P, V, T, C, those amino acids are present in this particular input peptide, okay? So that is what is shown here. P, V, T, C may be present in the input peptide, okay? So we will start with these 4 1-mer peptides PVTC, then we will, this is the initial candidate solution part, then we will branch and try to add one more letter, one more amino acid to each of these 1-mers, okay, to make it into 2-mers, okay? So we are going to branch it out, we are going to add all the other 20 letters to each one of them. Now we are going to see which one of these are consistent, okay, with the spectrum that is provided to us, with the input spectrum that is provided to us. What do I mean by that? We can look at some of these or each one of these 2-mers and see which ones are consistent, right? And then trim this list based on the consistent match between the mass of this and the mass somewhere here has to match. If it matches, you keep it, otherwise you ignore it, okay? So you just either keep it or ignore it based on whether the mass of this matches the reported mass in the spectrum, okay? To make things clear, let's just look at a specific example. Mass of P is going to be 97, mass of V is going to be 99, mass of PV is going to be 196, okay? Is 196 in this input spectrum? It is there, so I will keep PV, okay? And let's look at another example. CD, okay, mass of C is going to be 103, mass of D is going to be 115, so mass of CD is going to be 103 plus 115, that is going to be 218, and this 218 I can't see it anywhere here. This is in a sorted order. There is 200, 202, 295, right? There is no 218. So this CD I exclude and trim the list, okay? CD is not going to be included, okay? So if you go through all the 2-mers that you have and then trim away certain things whose masses do not match the input masses, then you are left with these consistent set of 2-mers that are shown here. And then these can then be extended or branched into 3-mers, and then again you can do a trimming operations to only retain 3-mers whose masses match the masses that are in the input spectrum, right? And so that is what we can do next. Expand, branch, and then trim, which is bound. And so you will have a list of consistent 3-mers that are shown here, and then extended by 1 more, and then you have the 4-mers that are shown here, and so on until you get these list of 5-mers. And this cyclic peptide, which is this PVCPT, right, that is exactly the one whose theoretical spectrum matches the input spectrum, okay? And then now you are done because all of these entries are now matching the different substrings of this one cyclic peptide. And so here is the pseudocode for the algorithm. You find all the amino acids whose masses occur in spectrum, you add it to the list, and then you extend each peptide in the list by each of the 18 different amino acid masses. So remember that there were 20, but then it was condensed down to collapse down to 18 because 2 pairs of amino acids have the same masses. Now you trim the inconsistent peptides from the list because their masses don't match the masses that are provided in the input. Then you again keep repeating this operation, this extending or expanding and trimming operations until you get a full length peptide whose theoretical spectra matches exactly the input spectra. So given this branch and bound algorithm, so how efficient is it in practice and how efficient is it theoretically, right? The dependence, the exponential dependence, right, on the number of peptides on the integer mass, right? So for instance, we saw that with this 1322 there were about 1 trillion peptides, right? So the branch and bound algorithm will allow us to not look at all those trillion peptides, but still it will have an exponential dependence in the worst case, okay? The algorithm will still run and it will still process all these 3-mers and 4-mers and so on, exponential number of them before it can figure out the full length peptide, okay? That will be in some data sets or some cases for certain masses, okay? But in practice, actually what happens is this branch and bound heuristic runs quite efficiently, right? In majority of the cases where it has been tried, it's typically very fast, but it's by no means a proof or anything. It's just an empirical observation, but there are definitely data sets where it will take exponential time, okay? So in practice it is very fast. Does that mean that we are done with the algorithm? So but like earlier teasings that we have done in the course, so this is definitely not the end of the algorithm because there are certain practical difficulties that we will encounter with the spectra, okay? The spectra, the theoretical spectrum that we have is not always cleanly observed, right? The actual mass spec instrument will give you erroneous spectra. Certain masses may be dropped and certain masses may not be correctly measured. So from an incorrect or noisy spectra, how can you figure out the actual peptide? Okay, that is what we need to look at next before we can really go home. Okay.